So hi everyone, in this video, I am going to discuss about an introduction to AVL trees. So last time we discussed about the performance of binary search trees. So ideally, the binary search trees should be complete and then full. So that means that the operations like searching, insertion, as well as deletion would run at O of height or O of log n. So what happens if the binary search tree is not balanced? So for example, here the binary search tree looks like a linked list. That means that at the worst case, the operations would run at O of n. Okay? So how can we possibly maintain the balance into the search tree so the operations would run at O of log n? Okay, so, well, there are some approaches to balancing trees. So we can opt not to balance actually. So we may end up with some nodes that are very deep, or we could have a very strict na balance wherein all the time the tree must always be perfectly balanced, or we could just allow a little bit of balance. So these AVL trees that I have mentioned earlier, or the Adelson-Belsky and Landis, are height balanced na trees and are one of the good but not perfect balanced na trees. Okay, so how does it factor the balance of a node? So it checks the height of the left subtree and then the height of the right subtree and take its difference. So an AVL tree has a balance factor that is calculated at every node, and for every node, the heights of left and the right subtree could can differ by no more than 1. Okay, so let's see. For example, this one, we have this tree on the left, wherein it's rooted at 6. And we know that at root 6, counting the number of edges from here unto the deepest na leaf, like 1 or 5, so it's 2. So the height of the tree is 2. At node 4, the height is 1. So because from 4 to 1 or 4 to 5, the max na number of edges is only 1. But for the leaves, 1, 5, and then 9, the height is 0. So the balance factor here at node 6 is 1, because we can uh, compute for the height or compute for the difference between the height of the left subtree, which is 1, and the right subtree, which is 0. And we can see that it's balanced. Okay, so the 3B, on the other hand, as you can see, it's also rooted at 6 here. And then, so it has a height of 2, counting the max na height from root 6 up to some certain leaf. And then at node 4 and at node 9, all ones. And then for 1, 5, and then 8, which are all leaves, would be 0. Okay, so for those that have empty na height, so for example, at this node 9, and then it doesn't have a left subtree and then the right subtree, so it has a height of -1. Okay, so for example, here again, assuming that on 3A, we added or inserted a new node on the left. And as you can see, the height of the tree here is still balanced. Okay, so even if we have added a new node 7, because the height of this node is still 0, and if we look at this compute for the difference between the height of the left subtree and then the right subtree of 9, still 1. Okay, just a 1 na difference. Okay, and if we look at every other node, and then the tree is balanced. But let's say how about for 3B? So for this tree, we have inserted a node 7 as a left child of 8. Now, we see that the left that the balance factor now is 2. So if we look at the left sub-tree of 9, and then the right sub-tree of this 9, and then the left sub-tree has a height of 1, uh, and then on the right sub-tree has a height of, no, sorry, 2, and then on the right as -1. So taking the difference, so it's equal to 2, and therefore this tree is no longer balanced. So that means that in this example, we have shown that insertion of a certain node may cause the balance factor to become 2 or -2 for some nodes. So only nodes in the path from insertion point to root node have possibly changed in height. So after the insert, so we must go back up to the root node by node, then we must update the heights. And if the new balance factor is 2 or -2, then what we can do is to rotate the tree or to adjust the tree around the node so the height, so we can balance the um, height of the tree again. Okay? So for example, here, so we know that on this certain node, at rooted at 9, there is some imbalance in the tree. So what we can do is apply a single rotation, wherein in this subtree, now the 8 is now on the root. The 8 is now on the root, and then now 9 becomes its right na subtree, and then 7 on its left na subtree. So only one na rotation or single na rotation. Okay? So in the next video, I am going to discuss more about insertions in the AVL na trees.